Derivation of Navier Stokes momentum equations. The equation shown is the compressible Navier Stokes momentum equation for Newtonian fluid. So it comes from applying Newton's second law, Cauchy's Cauchy stress theorem, conservation of momentum, and Newtonian constitutive law. So this is rho times acceleration. So we have the rho here times F, and we have the viscosity times the Laplacian of V minus 1/3 of the gradient times the divergence of V minus minus the gradient of the pressure. So Newton's second law for fluid, for a moving fluid here, mass times acceleration equal to the sum of forces. So mass per unit volume is rho. Acceleration of fluid, the particle is the material derivative. Derivative of V with respect to time. So this is the velocity. That's the mass per unit volume multiplied with this acceleration is equal to the net force. Equal to the surface forces plus the body forces. We have the body forces here. Example of the body forces are gravity, electromagnetic force. So denote the body force per unit mass by F. Then body force per unit volume is rho times F. We have the surface of forces here and a stress tensor from Cauchy's stress theorem. Surface force per unit volume equal to the this is what we call the divergence of the stress tensor. So this one is the stress tensor. Thus, momentum conservation becomes this net force equal to the divergence of the stress tensor plus the body force here. So this is the general momentum equations. Decompose the stress tensor here for fluids equal to the negative of the pressure times the identity tensor plus the viscous stress tensor. Then we have the divergence of the stress tensor here by substitutions here. So we have negative the divergence of negative P times I equal to the negative of the, this is what we call the gradient of the pressure. Thus, the net force here is equal to the negative of the gradient of the pressure plus the divergence of the viscous stress tensor plus the body force here. So Newtonian fluid constitutive law for a Newtonian fluid here. So this is the equations. So this one is the transpose of the. So we have the dynamic viscosity. So we have the multiplied by the gradient of V plus the transpose of the gradient of V minus 2/3 of the viscosity here, dynamic viscosity, times the times the divergence of V here times I, the stress tensor. So the text explains that the transpose of the gradient of V, or specifically pairing it with the gradient, writes symmetric mathematical objects. Basically, this symmetry ignores how the fluid rotates and focuses only on how the fluid changes shape. So this is crucial because rotating does not dissipate energy, but deforming, stretching, or shearing creates internal frictions, viscosity, and changes the shape of the fluid element. So take a divergence of viscous stress, applying vector calculus identities here. So substituting it into the general momentum equations here. So we have this. But in the standard textbook conventions, if you look at almost any fluid dynamics textbooks, White, Kando, Bachelor, or the standard Navier Stokes equation, you will find the compressible form written as this one. So this is negative. Now here we have the positive here, but this one is negative. So this is the industry standard. So why is it negative? So we'll discuss that. Physical intuitions, the stabilizing effect here. Physics dictates that viscosity precedes the deformations. So we have for the compressions, if the divergence of V is less than zero, if fluid particles are getting closer together, the compression term, this one, becomes negative. So we have the negative here times this is also negative because it decreases. So this becomes positive. So if that is positive, this produces positive pressure pushing outward against the compression. The compression. So expansion, if the divergence of V is greater than zero, if fluid particles are spreading apart, the term becomes positive. So negative terms positive go to negative. So this produces a negative pressure, pulling the fluid back together. Because if uh, if if this is the expansion, so that's positive, but the pressure is negative, pulling the fluid back together here. So in both cases, the negative sign ensures the viscous force always opposes the volume change, stabilizing the flow. So the right side here, the first term, this one is the represent the diffusion of momentum via shear viscosity. We have here the dynamic viscosity. The thickness resistance of the fluid. And this one is the Laplacian of velocity, the curvature or spatial change of the velocity fluid. So we have the physical meaning here. So this term governs how momentum spreads out like heat in a pan. It causes velocity differences to smooth out. So, for example, here, if you drop a spoonful of honey into a larger bowl of honey, this term is responsible for making the honey stop moving and eventually match the speed of the rest of the fluid. And we have the right side, the second term here. So this one, we have the divergence of velocity. So this measures how fast the fluid is expanding or compressing. So we have already discussed this, but let's review this one. So we have the gradient operator. We have the physical meaning. So this term accounts for extra viscous force when the fluid volume changes, compresses, or expands. It arises from Stokes' hypothesis, which links bulk viscosity to shear viscosity. So this term often neglected if the fluid is incompressible here, like water, because for incompressible flow, the divergence of V is equal to zero. So making this whole term adds up here. So the term one, which is the divergence of velocity, for our review, if this is greater than zero, the fluid is expanding. Now, if this is less than zero, is the divergence, the fluid is compressing, converging. So viscosity is the friction of the fluid. It always acts to resist changes in motion. So because of this resistance, if the fluid is expanding greater than zero, the viscosity creates a negative pressure, pulling force to slow down the expansion. So if the fluid is compressing less than zero, the viscosity creates a positive pressure, a pushing force to resist the compression. So meaning of each term, so this one is the fluid acceleration. We have the right side here. This is the body force. Then we have the viscous diffusion here, this one. So it represents the momentum diffusion due to viscosity. similar to heat diffusion. We have the compressibility correction here. This one, it appears incompressible flow. So if flow is incompressible, so this one is equal to zero. So this term vanishes. So we have the pressure force here. So fluid moves from high pressure to low pressure. We have the material derivative, this one. So, so this is the acceleration. There's the unit mass here. So this is the net force. We have the gradient of pressure here plus the Laplacian of V minus 1/3. Now this is the gradient of the divergence of V plus the body force here. Now for incompressible form, let's again review. The divergence is equal to zero here. Then the equation simplifies to this if this is equal to zero. So this is the most famous form of the Navier-Stokes equation. Yes, and CFD. This is the fluid dynamics, aerodynamics, weather simulations, ocean currents, earthquake fluid models, heat transfer. We have the console here, Mathematica, with the solvers. We have the velocity field here. So we have a small value for viscosity here. We have also a small value for the flow amplitude. So it refers to the velocity of the water, of the fluid here, flow amplitude. Then we have the vortex strength. Now let us see the simulation. If we increase the viscosity here, so what will happen to the simulations? So if we increase all the quantities here, so we increase the vortex strength here, also the flow amplitude by decreasing the viscosity, can also decrease the velocity of the water, of the fluid, and also the vortex strength here. So what this simulation represents, uh, the displayed the velocity field approximates decaying viscous vortex flow. So the Navier-Stokes momentum equation is this one. So this example demonstrates mainly the viscous diffusions, transient flow decay, stational fluid motion through this term e to the negative of the dynamic viscosity times time, which model viscous damping. So being our controls here, viscosity, higher viscosity damps motion faster, smooths the flow. Similar to honey, high viscosity, water, lower viscosity. We have the amplitude controls, uh, fluid velocity magnitude. We have the vortex strength here. Controls are rotational circulation density. So what does stem lines mean? The blue curves here represent the fluid vector velocity, vector field. Represent the direction shows the flow directions. The density shows flow intensity. We have the explanation of the code here. So I will not discuss this anymore.